Mean, hopefully when you think of mean, whenever I tell you mean, you think of average, right? So in the past, you were given two numbers, A and B, and you did A plus B, and then you divided them by 2 because there's two numbers. That would be the average, or the arithmetic mean. Where arithmetic sounds like arithmetic, right? So the arithmetic mean. This is the geometric mean. Well, I mean, it means average. So this is similar process, but it's different because this is the geometric mean. Instead of adding two numbers together, you're going to take the product of two numbers. So you're going to multiply two numbers together. And instead of dividing by 2, you are going to take the square root. All right? So this is going to be the square root of A times B equals the geometric mean. All right, so that's the difference. So at first we're just going to find the geometric mean of two given numbers. We're given the numbers. Thank you. And since we're going to simplify radicals, I'm going to make a list on the side of the first 10. I have 4, 9, 16, 25, 36, 49, 64, 81, and 100. So there's the first 10 perfect squares, minus 1, of course. So to find the geometric mean of the pair of numbers, I'm going to call that x, it equals the square root of the product of those numbers. So x equals the square root of 4 times 25. Now, like what we went over yesterday, we could either multiply those together and take the square root, or we could take it separately. Anytime I see a perfect square, I like to go ahead and take the square root of that number before multiplying. So if the square root of 4 is 2, and the square root of 25 is 5, then x equals 10. Or if I multiplied them together, 4 times 25 would have been 100, and the square root of 100 is 10. So either way, I would have got to the same answer. But whenever you do the geometric mean, if you see a perfect square, go ahead and take the square root of that number. All right, so number 2, x equals the square root of 5 and 30. Okay, so neither one of those are perfect squares. So that means I need to multiply them together. Square root of 150. And now, like the process I went over yesterday, I start with the largest on my list, and I'm going to divide 150 until I get a whole number. It divides evenly. So 150 divided by 100, no, that won't work. 150 divided by 81, that's a decimal. 150 divided by 64, that gives me a decimal. 49, no. 36, no. 150 divided by 25, yes, that does divide evenly. So I'm going to split this up into the square root of 25 times the square root of 6, because 150 divided by 25 is 6. So all I did is I changed 150 into 25 times 6, and the radicals are still there. And now I have a perfect square, 25. And the square root of 25 is 5. And I can't do anything with the square root of 6. I can't simplify that any further so that I'm finished. So it's 5 square root of 6. Okay? All right, so number 3, x equals the geometric mean of 2 and 8, so 2 times 8. Neither one of those are a perfect square, so I'm going to multiply them together. So x equals the square root of 16, and that just worked out nice and lovely. Square root of 16 is 4, so x equals 4. Last one, 7 and 15. So x equals the square root of 7 times 15. Neither one of those are a perfect square. X equals the square root of 105. And then I go through my list of numbers. Is there a perfect square that will divide 105 evenly? Let's try all of the values. 105 divided by 81, no. 64, no. 49, no. Nope, all the way down to 4. It still gives me a decimal. None of those values will give me a whole number. So that means I can't simplify it any further. That is the simplest version of that radical. And if you wanted to check that with a factor tree, it's actually not too bad to check. 7 is already a prime number. 15 can be broken down into 3 times 5. And those are both prime numbers. So I have 7, 3, and 5. There's no pairs. So 105. All right, so that is how to do the geometric mean when you're just given the numbers. But sometimes you're not given the numbers. And we have this corollary, which is something that goes along with a theorem. The part I'm not really spending any time on is the fact that all 3 of these right triangles are similar. I'm kind of doing it as a given statement. All 3 right triangles in this picture are similar. So that's like our given information. Because you could take these triangles and turn them around so they're all facing the same direction, and then you could say they're right similarity statements saying that each piece is similar to the other piece. But we're not going to really do that. Make sure you can see the 3 triangles I'm talking about. There's the large right triangle, okay? And then there is a medium-sized right triangle. And I also have a smaller right triangle over here. So that's the 3 triangles I'm talking about. And we can use geometric mean to find the lengths of the legs and altitude of the large triangle, which I'm highlighting in 3 different colors. So these 3 pieces, okay? So I could set this up as A, if I want to find that piece. A equals the square root of the product of 2 numbers. H, same thing. And B, same thing. And I'm going to Alright, so those are the 3 pieces that equal the geometric mean of different parts of the large hypotenuse, depending on what we're working with. So A, the yellow line, equals the geometric mean of the 2 parts of the large hypotenuse that is touching, X and C. Alright, so you can see the green line is the entire length of the large hypotenuse, and that's C. And the red line, X, is a leg of the small triangle. So A equals the geometric mean of X and C. X times C. Because A, the yellow line, is touching the red and the green in that corner. That is the 2 pieces that are touching the same corner as that piece of the triangle that we're talking about. The same with H. But H is touching X and Y. It's not touching C. I mean, in a way it is, but I have it drawn this way on purpose, where X and Y are on the inside and C is on the outside. Because C really is X and Y added together, so H is kind of touching all of it. But the way I have it represented here, H is blocked off by the red and the blue line, and it doesn't get to the green line. So I'm going to use X and Y. And then the last one, the other leg of the large triangle, B, the light blue, is touching Y, the blue line, and it's touching C, the green line. Alright, so I'm going to have that triangle drawn on the board, or I actually have it already drawn on the board over there, and I'm not going to erase it. I'm going to leave that there. Hopefully that helps you. But this is what we're going to be looking at for geometric mean. Okay, so we have to identify what we have and what we're looking for. So in the first triangle, this X is like the yellow piece. And the reason I use colors is because depending on the variable that you're solving for, and there's already an X in my diagram, it gets confusing if I say X, A, B, C, Y, whenever those letters are already in the picture. So I'm going to call that the yellow piece, and it's going to be touching the red piece and the green, because that's the formula for yellow, is yellow equals the geometric mean of red and green. But I don't have anything given for the green. But I have the red and the blue, and the red and the blue together make the green. So if I add 3 plus 9, that's 12. I know the total length of the large hypotenuse is 12, because if I add those two pieces together, that's what makes that line. And now I can set up my problem. X equals the square root of 3 times 12. And from there, I'm just going to solve it. So with 3 and 12, neither one of those is a perfect square, so I'm just going to multiply them together. X equals the square root of 36. Very nice. That is a perfect square. So X equals 6. That one's nice and easy. There's nothing tricky there. It all depends on what you have and what is missing. Sometimes the variable is on the left, the A, the H, and the B. Sometimes it's inside the radical. It just depends on the problem. I think that the bright green highlighter piece is the easy one to see. It's the only line that goes through the triangle, right? So it's pretty obvious which one that one is. So that means the other two have to be red and blue. Alright, so that is this is solving for H. So X equals the square root of 2 times 4. Alright, 2 is not a perfect square, but 4 is a perfect square. So I'm going to go ahead and take the square root of 4. So the square root of 4 is 2. That comes to the outside. The square root 2 has to stay inside because I can't simplify that any further. So this one is X equals 2 square root 2. Okay, so then on the back I have some more. Alright, so Z, leg of the long of the medium triangle. And that one becomes blue. But when I have an outside piece, an outside leg of the large triangle, then I need the total length of the hypotenuse also. So I have the two pieces. If I add them together, 7 plus 2 is 9. So that total length is 9. So then Z equals the geometric mean of 7 times 9. Look for perfect squares. 7 is not, but 9 is. So you can take the square root of 9. So then Z equals 3 times the square root of 7. And I cannot simplify the square root of 7 anymore because the square root of 7, because 7 is a prime number. It can only be divided by itself in 1. So Z equals 3 times the square root of 7. Okay, the next one. Alright, so that leg of the large triangle is going to equal the geometric mean of the two pieces that it's touching. so that means that 7 this time is on the outside. And it's going to equal the square root. Okay, so 7 is on the outside of 4 times x. So now my x is inside the radical. So my solving is going to require a little bit more. But I'm going to go about it in the same way. So the square root of 4, that's a perfect square. So the square root of 4 is 2. So 7 equals 2 times the square root of x. I'm trying to get x by itself, so I'm going to divide by 2. I'm going to leave that as 7 over 2 for right now. I'm not going to get a decimal. I'm going to leave it as 7 over 2. Because the whole idea of simplifying is we want exact values. We don't want decimals. Decimals are less exact than fractions. All right, so I'm going to bring this up here. So 7 over 2 equals the square root of x. Now I need to get rid of the radical because I want to get x by itself. What is the inverse operation of a square root? Basically, how do I cancel out a square root?
Square it?
Yeah, exactly. You square it. Because if you look at the list of numbers, like 2 squared equals 4, the square root of 4 equals 2. So it's going in the undoing the square root is squaring it. So to cancel out the square root, square the whole thing. If you do it on one side of an equation, you have to do it on the other side as well. We'll get to that in a second. So the square root and the squared cancel each other out. Now I have x on the right. And now I need to square a fraction. But squaring a fraction, it's not that big a deal. Just like when we simplified radicals yesterday, you can treat the numerator and the denominator separate from each other. So we're going to have 7 squared on the top is 49. And 2 squared on the bottom is 4. And that's it. You square the top and square the bottom separate. Nothing really tricky there. So x equals 49 over 4. All right. A couple more examples. All right, number 5 is the altitude of the large triangle. So one that goes through the middle. So we're going to use the 2 pieces it touches, the 3 and the x. So 9 equals the square root of 3 times x. And I can't take the square root of a 3, and I can't take the square root of x. So I'm just going to start with squaring it. Just get rid of the radical. It's the only thing I can do here. So put the whole thing in parentheses and square it. You have to square both sides. So the radical and the squared cancel. And 9 squared is 81. So 81 equals 3x. If I'm solving for x, means I want x by itself. I have 3 times x. So to undo multiplication, I use division. It's the inverse operation of multiplication. 81 divided by 3 is 27. So x equals 27. All right. Next example, number 6. Now this is a lot of the same kind of examples, but it's worth going through them. So there's one piece, and then what touches the corner where they meet? I need 2, so I need the green one also. So this becomes 10 equals the square root of 2x. To get rid of the radical, I'm going to square the whole thing. Square root squared cancel. 10 squared is 100, and that leaves 2x. So this has actually turned out to be pretty easy. I want x by itself, so I'm going to divide it by 2. So x is 50. All right, I'm going to go through two more examples. Number 7, it's on the side again. It's the yellow line, and then the red line goes with it, and the green line. I'm not given the green line, but I know if I add those two together, if I add these together, then it's 20. So there's my equation. So x equals the square root, or the geometric mean, of 5 times 20. Since neither one of those is a perfect square, I'm going to multiply them together. So x equals the square root of 100. And now I do have a perfect square. Not every time, but this time. So x equals 10. The last one is the altitude of the large triangle. Goes through the middle, so I'm going to use the two pieces it touches, the 5 and the x. So 10 equals the square root of 5x. To get rid of the radical, I'm going to square it. I'm going to square both sides. And then that cancels the radical and the squared. So 100 equals 5x. And the last thing is to divide by 5. So 20 equals x.